In this video, we will look at the region of operation of N-type MOSFETs, and this is a very common question in gate examination for either instrumentation engineering or electrical engineering, as well as for electronics and communication paper. So this is the circuit symbol for the N-channel MOSFET, and you will find that the arrow points outward towards the source terminal for this NMOS. This is the gate terminal, here is the drain terminal, and this is the source terminal. And generally the body or the substrate terminal is not shown in a circuit symbol like so. This is the physical construction of the N-type MOSFET. Here you have the presence of 4 terminals. So here is the source terminal, here is the drain terminal, this is the gate terminal or the control terminal, and this is the body or the substrate terminal. So substrate is what it is. So with an N-type MOSFET, you have a P-type substrate and the body terminal is connected here on. You have two N plus doped regions, and one of them is connected to the source, another one is connected via metal contacts to the drain terminal, and then you have the gate terminal, which again uses a metal contact, but between this semiconductor layer and this metal there is presence of an oxide layer which acts as a dielectric or an insulator. Hence the term metal oxide semiconductor. And operation wise, you can also think of this as a capacitor. Okay. Next, we look at the drain to source voltage versus the drain current or drain to source current of the N-channel MOSFET for various values of gate to source voltage. So this is gate to source voltage of 0 volt, 1 volt, 2 volt, 3 volt, and so on. Now note that this is obeying 3 different segments of behavior. The first segment is this one right over here, where VGS is less than the something called as threshold voltage. VGS is less than VT. VT stands for the threshold voltage. So unless you can apply sufficient voltage between gate and source, the channel formation between the source terminal and the drain terminal, so the channel formation takes place here, that channel will not be formed. And so you need a minimum of VGS to be equal to VT for formation of the N channel. So that N channel will provide a path for flow of conduction of electrons. So this region is called as cutoff region, where you are applying a voltage between gate and source which is less than the threshold voltage VT. Now no matter what you do with VDS, even if you keep applying VDS, but if you are using this condition where the threshold voltage is not reached by the gate to source voltage, then no current flow will take place between the two terminals of the N MOSFET. So that means the source and the drain will behave as an open switch. Then you have this region which is called as the triode region, and somewhere close to this origin you have a proper ohmic region. So the MOSFET can behave as an electronic resistor in this region, and this entire region is called as the triode region. So in triode region, the condition is that first of all you have to establish the conduction of the channel. So that means we can now allow current flow to take place through the transistor, which implies that from drain to source current flow will take place because the electronic movement will take place from the source to the drain terminal. But the other condition is that the drain to source voltage should be restricted to a value which is smaller than VGS minus VT. So whatever these points are, these are always equal to VGS minus of VT. So for instance, this point will be 1 volt minus of Vt, this point will be 2 volt minus of Vt, and so on. And then finally you come up with a region which is called as the saturation region. So in an ideal N-MOSFET, this current is independent of the drain to source voltage, whereas in a practical N-MOSFET, there will be some inclination, which implies that there is some resistance associated with the constant current source. So here, this is a practical diagram for the VDS versus ID characteristic shown here. So this implies that in this region, we can model the N-MOSFET as a current source along with a resistance in parallel to it, although the value of that resistance will be pretty high. In an ideal case, these lines will be absolutely parallel to the x-axis and you get an ideal current source. So with the saturation region, the condition is that you have to establish the inversion layer. So VGS should be greater than or equal to VT. And the other condition is that VDS, that means drain to source voltage, should exceed the overdrive voltage, which is also called as VGS minus of VT. So this is something we have to keep in mind if we are to solve any question related to identifying the region of operation of the MOSFET. So let us look at some problems on how we can find out the region of operation of the N-channel MOSFET. In this question, the threshold voltage is mentioned to be 0.4 volt, and our objective is to find out, given that these are the voltage conditions applied to the drain terminal, source terminal, and the gate terminal, whether the N-MOSFET is in cutoff region, whether it is in triode region, or whether it is working in saturation mode. So the way to go about it is we have to find out the drain to source voltage and the gate to source voltage and then make a comparison between VDS and VGS minus of VT, provided VGS is greater than or equal to the threshold voltage. So let's look at problem number A. Here the drain voltage is equal to 0 volt because it's grounded. Gate voltage is also equal to 0 volt, it's grounded, and the source terminal is at 1 volt. And so we can formulate VGS as VG minus of VS. So this is equal to negative 1 volt. And as soon as we obtain negative 1 volt and we are comparing it with the threshold voltage of 0.4 volt, we find that this diode has not generated any channel between the source and the drain terminal because VGS is less than the threshold voltage of VT. And therefore we can go on and say that this particular MOSFET is in cutoff region. Okay, next question. In this question, the drain voltage, we can see that this is at 1 volt. The source terminal is grounded, as well as the gate terminal is also grounded. And therefore, VGS, gate to source voltage, is equal to gate voltage minus of source voltage. And therefore, it's 0 minus 0, which is equal to 0 volt. Once again, like the previous example, we find that the channel formation will not take place in this NMOS because it is not greater than or equal to the threshold voltage of 0.4 volt. So for this problem also, this MOSFET is in cutoff region. Let us look at the third example. Here the gate terminal is at 1 volt, the drain terminal is at 0.2 volt, and the source terminal is at 0.2 volt. So drain and source voltages are same. Now has channel inversion taken place? And we find that gate to source voltage is equal to 1 volt minus of 0.2 volt. So this is equal to 0.8 volts. So VGS should be equal to 0.8 volts and it has exceeded VT. So the channel formation has taken place between source and drain terminals. Now let us look at the condition of VDS and VGS minus of VT. So we know that VGS is equal to 0.8 volt and VT is equal to 0.4 volt, and therefore the overdrive voltage is equal to 0.8 minus of 0.4, which is equal to 0.4 volt. But on the other hand, the drain to source voltage is equal to 0 volt because the drain terminal is at 0.2 volt, source is also at 0.2 volt, and therefore this is equal to 0 volt. VDS is equal to 0 volt. So if we make a comparison between VDS and VGS minus of VT, we find that VDS is less than 0.4 volt. So 0 volt is less than 0.4 volt, and therefore it satisfies our condition of triode region of operation. So this MOSFET is operating in triode region. So this is the basic concept. Now, as a practice problem, you can try to solve for this question where the gate terminal is at 1 volt, the drain is at 0.2 volt, and the source is at 0.7 volt, and you can try to identify the region of operation. So in this lecture, we looked at the region of operation of the N-type MOSFET. In our subsequent lectures, we will look at the region of operation for the P-type MOSFET. But the general idea is more or less the same.